Just just like my classes, I'll be talking for 5 minutes, and I'll finally somebody in the chat will say, "Your mic isn't on." So, well, welcome to my world. Okay, I am Dr. Cotter from Old Dominion University. I'm with the Engineering Management Systems Engineering Department at ODU. Been there for 18 years. Yeah, 18 years now. Time flies when you're having fun. Um, my research interests are digital engineering, informatics, AI, human knowledge engineering, specifically ontology development for Industry 4.0, cyber technical, socio, quality, reliability systems, design, engineering, and management. Uh, what will quality systems, quality reliability systems look like under Industry 4.0 cyber physical systems architectures. And then finally, computational systems, computational systems dynamics engineering, specifically using Bayesian hierarchical state space models. What are the dynamics? How do the cyber technical socio, notice I use the term cyber technical socio, following on from Milt's observations that all of this, we talk about AI, we talk about the nine technologies of the Boston Consulting Group being core of the core of cyber physical systems, but ultimately it's going to happen within organizations. So interest there is how do the cyber physical, which I call cyber technical, because there's a difference between physical and technical. Technical, using Simon's definition of the artificial, is created by humans, whereas you can still have the physical world that's not created by humans. But the cyber technical, quote, social integration of the cyber, the intelligent smart systems into our work processes or into our society. So I want to welcome you to the ASQ Statistics Division Quality 4.0 conference. This discussion presents the human factors analysis and classification system as a systems framework for understanding the causal factors for understanding systemic latent failures that accumulate in product failure. In this case, I'm just using aircraft accidents as the product, or the aircraft as the product. In this discussion, we'll present the theoretical foundation of HFACS. Chat, quick feedback, look at Mike. I'll continue with discussion. Is anyone familiar with HFACS and has a background with HFACS? So we'll present the theoretical foundation of HFACS. Oh, I'm talking HFACS, Human Factors Accident Classification System Framework, and is based on the Federal Aviation Administration summaries that apply to the Lion Air 610 and Ethiopian Airlines Flight 302 accidents and the January 2024 grounding that resulted from the mid-flight blowout of the unused emergency exit plug on the Alaska Airlines jet. Finally, I'll propose adaptation of HFACS framework to become the systemic basis for Industry 4.0 intelligent cyber physical systems failure analyses. Discussion. We'll start out with what we all know. What are the standard quality failure analysis techniques? And they have their strengths, but they also have their challenges with respect to the upcoming Industry 4.0 architecture. Then we'll discuss the human factors analysis and classification system, the theoretical basis, the taxonomy. It has a formal taxonomy, the accident investigation protocol. Then we'll look at the Boeing 737 MAX crash and grounding HFACS analyses. Then we'll apply that to future Industry 4.0 failure analyses, the Industry 4.0 Internet of Things, RAMI model, For those of you who may not be familiar, that is an evolving model out of Europe, primarily Germany, that's designed to support the Internet of Things. The industry proposed Industry 4.0 HFACS failure analysis, and then the failure modeling recommendation. So standard quality failure analysis techniques we're all for. If you're a quality professional, been around as long as Milt and I have, you've studied these multiple times. But the Ishikawa fishbone diagram, 5 whys, cause and effect analysis, causal factor tree, failure modes and effect criticality analysis, FMECA, fault tree or fault logic tree analysis, barrier analysis, and then of course the Kettner-Trigo change analysis. For manifest factors, the standard quality failure analyses really work best with manifest factors and the variables that have direct causal impact on the output Y quality characteristics. So this is the typical transformation, it's the Six Sigma transformation. If you have a background in control theory, do the Laplace transforms. This could then be the typical transform, Laplace transform process. So we have some inputs, x1 through xk. These are materials, information, human, other resource inputs, energy inputs. They all have characteristics, and they all have that little error term attached to them at the end. So when we do the Y equals f of x, the Y being the vector or the matrix of quality characteristics that we ship to our customers, that transformation, we also transform the epsilon error term not shown here. So finally, the Y itself, notice it's bolded, that recognizes that the customer receives a vector or a matrix of quality or functional performance characteristics that in some way resemble the behavior of how they want to use our products or services. So the key takeaway here is for quality, the previous quality failure analysis techniques, since they're human driven, they really work best for manifest direct causal impact input variables. Standard quality failure analysis techniques tend to break down on latent factors and variables that have moderating or mediating hidden impact across organizational boundaries on the output Y quality characteristics. So on the left, for those of you who are familiar with moderating and mediating regression, these are standard diagrams. On the left, we have the moderating hidden variable. We have the Y equals f of x transformation. And in this case, the moderator affects at least one, jointly affects at least one of the x inputs and at least one of the Y outputs. So that's a moderator. Prime example is years ago I had a measurement system analysis problem, and one of our facilities in New Jersey, the facility here in Virginia and the facility in Maryland had temperature humidity control labs. The facility, our customer's facility in Minneapolis was well, not completely temperature humidity controlled, and it had some swings. So temperature and humidity affected both the measurement, the preparation of the sample, and the actual measurement of the Y output. That was a moderating variable. The lab in our New Jersey facility was in an old building with only non-insulated cinder block walls, so it had a lot of variation. On the other hand, the hidden mediating variables, at least one of the Y's affects the hidden mediating variable, the Z, and that in turn affects or X affects the Z, and the Z in turn affects the Y. Yes, do I have a note out there? Did somebody say something? Maybe that was just Mike's microphone on. So this is where the standard failure analysis technique tend to break down and where HFACS can come in. So what is the human factors analysis and classification system? It's based on James Reason's Swiss cheese model. That's the next slide. Accident causation, and was designed to define the holes in the Swiss cheese, facilitating the application of Reason's model to accident investigation and analysis. This comes out of Wegman and Chappell's 2003 article. So Reason's 1990 accident causation model is a theoretical model that seeks to explain how accidents occur in organization and among its levels. Now, this is perhaps going to be absolutely key for later discussion of HFAs or of Industry 4.0 technologies. It is based on two assumptions. Assumption one, accidents occur in such a way that the manifest and latent causes have relationships with other levels of the organization. So it's a multi-layered approach. The components are analysis. The components of organization need or are obliged to function together at minimum to prevent accidents. Accidents do not occur independent of the organization itself. Going to move. No, I'm not going to move it over. So this is Reason's model. We have all of the Swiss holes in the Swiss cheese have to line up from the organizational level. There's failure decisions, line management deficiencies, preconditions for an accident, unsafe acts, and the deficiency itself that lead to an accident. So notice that the higher ones, and I apologize for the clarity of this, but I took it from an article. So we have latent attributes and we have the active latent failure. So we're really looking at it from a latent point of view, and the manifest can be modeled directly. So the taxonomy, now when I say taxonomy of HFACS, originally the U.S. Air Force, U.S. Navy developed a formal taxonomy with definitions of accident outcomes, their causes, and how those causes should be assigned within the HFACS. So this is a formal taxonomy. So the taxonomy of HFACS been used by the United States, U.S. Department of Defense, primarily the U.S. Air Force and the Navy, and it's also in use by the U.S. Army Air Corps and FAA with slight changes made through the levels and sub-levels, and we'll look at them in a slide or two. So additionally, the HFACS framework has been applied to a variety of industries, including mining, construction, rail, and healthcare. Healthcare has really picked it up if you look at the literature in the last 10, 15 years. So this is the Swiss cheese model adopted for the HFACS taxonomy. So we have organizational influences that permit, they are latent failures that permit the potential for unsafe acts. We have unsafe supervision, preconditions for unsafe acts, and then the unsafe acts themselves, leading to the active failures. So the unsafe acts themselves typically are the manifest, those that we can go out and through our typical 5Y analysis, FMECA, Ishikawa diagrams, those are the ones we can easily identify. It's the latent failures that typically escape our current failure analysis methods. So this is the HFACS taxonomy. It has organizational influences. That includes resource management. We'll do some definitions in the next few slides. Organizational climate, organizational processes, unsafe supervision, inadequate supervision, planned inappropriate operations, failed to correct known problems, and then pure supervisory violations where they knew there was a potential failure mode and allowed it to exist. I'm sorry, that's incorrect. That's the intentional supervisory violation for other opportunities or other issues. Environmental factors, physical environment, technological environment, condition of operators, adverse mental states, adverse psychological states, and physical or mental limitations. And then personal factors, this gets into crew resource management, how the crew is managed on and off, and then personal readiness. Then finally, the manifest unsafe act itself. It can come from decision errors, skill-based errors, perceptual errors, routine errors. We have a routine. We'll see, we won't see that, but we have a routine, we follow it, and we ignore the potential for unsafe or that accident. And then exceptions, which is kind of a catch-all. Now, notice the arrows are pointing down. The key takeaway here is all possible combinations of routes through this taxonomy are possible. So there are actually 420 possible combination routes through the HFACS taxonomy to go from organizational influence to unsafe supervision to precondition and our unsafe acts, and then the unsafe act itself resulting in an accident. Are we okay? Anybody, just a little verbal feedback. Has anybody used the HFACS before or are familiar with it?
No.
Okay, we have one out there. There's always one in every crowd. Okay. You want to add anything to the discussion? This is not just Steve Cotter's discussion. Okay. Okay, so that's our taxonomy. We'll start out at level 4 and work our way down. Organizational influence, resource management. This is organizational level decision making regarding the allocation and maintenance of assets, human resources, monetary budget resources, equipment facility resources. So again, as Milt was indicating earlier, it all comes back to management's measurement of the organization. And sometimes HFACS recognizes that the way we allocate our resources opens up the latent potential for failure. Organizational climate, this is the working climate, the structure, the policies, the culture itself. I was always surprised. I started out in industry a long time ago, and I went into supervision when I was still in undergrad school. One of the first things I noticed at one of my earlier employers, and I've noticed in every employer since, every department tended to have its own personality or culture. And those personalities and culture tended to remain stable over time, even though the employees in that department turned over. Likewise, I noticed going from company to company to company over the years before I joined ODU, they have their own overall corporate culture and personality. And these corporate cultures and personality sets up climates, latent climates for accidents or failures. Operational processes, these are decisions and rules that govern the everyday activities, and they come out of the policies. So it's not surprising that operational policies, procedures, oversight, or lack thereof is driven by the organizational climate. So that's the HFACS level 4, the top level, unsafe supervision, the next level. Inadequate supervision, providing staff with the opportunity, providing staff with the opportunity, guidance, and training and incentives to ensure the task is performed safely and efficiently. I should probably clarify that by saying not providing staff with the opportunities, guidance, etc. Plan inappropriate operations, operations that can be unacceptable during normal operations. In other words, we have insufficient planning and documentation of our operations. We fail to correct known problems. Deficiencies are known to the supervisor or supervision, but are allowed to continue unabated because it's got a real small probability of ever occurring, or whatever reasons. We just don't correct known problems. And then supervisory violations. These are existing rules and regulations that are willfully disregarded by supervisors for whatever reason. Level 2, precondition for unsafe acts. The physical environment, the operational setting and ambient environment in which we work. As a quality professional, particularly with visual inspection, we know that the lighting, the direct lighting, the ambient lighting, the structure of the work environment, all contribute to the ability to do visual inspection or to perform inspections. Same thing for unsafe acts or failure modes. Technological environment. This is getting over to the design and automation issues. And the technological environment will become even more important as the Industry 4.0 smart cyber technical socio or smart technical solutions are entities are integrated into the organization. Adverse mental state, these are mental conditions that affect performance. Maybe you're just having a bad day. Maybe there's some local politics within the organization, but these are mental conditions that can affect performance. Adverse psychological state, these are medical or psychological conditions that affect performance. These tend to be personal issues that are not adequately managed by supervision. Physical mental limitations, an operator lacks the physical or mental capabilities to cope with the situation, and this affects the performance itself. Continuing on, crew resource management. This is communication, coordination, planning, and teamwork issues, particularly important in the cockpit of aircraft, where the time off, the assembly of the crew to work in that particular aircraft, and crews are certified by a flight aircraft. Personal readiness, this is the off-duty activities required to perform optimally on the job, such as adhering to crew rest requirements, alcohol restrictions, other off-duty mandates. Now, quite often, I notice this in industry, we as supervisors were not taught to help our personnel manage their off-duty time so that when they came to the job, they were ready to transition into the job and work effectively and efficiently and safely. So that's the three levels of latent failures, organizational influences, unsafe supervision, precondition, unsafe acts. Now the manifest failures, which is what we typically can get at in our current failure mode analyses, the unsafe acts themselves, skill-based errors, errors which occur in the operator's execution of a routine that make an unsafe situation. Quite often, and especially this is when I had I'm coming at this from a background in HFACS. I had a doctoral student in 2014, up to he graduated in 2014, and his dissertation, some of which this is coming from, was on modeling or developing an SEM model to predict aircraft failure, manned and unmanned aircraft failures. And he went out and did the formal training on the taxonomy, come back, and we trained other personnel, and then we downloaded, I forget how many hundreds of aircraft incidents and accidents he downloaded. They classified all of those. We worked through the formal teams process of negotiating differences, and then the classification when he did multiple SEM models to demonstrate, then we could then use SEM to predict aircraft accidents based on the levels of the HFACS. So decision errors, these are behaviors or action of operators proceed as intended, yet the chosen plan provides proves inadequate to achieve the desired end state and results in an unsafe situation, i.e. an accident or an incident or an accident. An incident is a near miss, whereas an accident, for instance, recently we've had near misses where two planes came close to each other on the tarmac. Or we had a recent incident where they had a plane getting ready to take off and they had to have another airplane divert to avoid a crash. So those are incidents, and then, of course, accidents. Perceptual errors and operator sensory input is degraded, and a decision is made based on faulty information. And I think I left out, let's see, I left out, that's the errors. Violations are clear. We had a routine that wasn't followed, or there was an exception to a routine, and they developed the best solution they could, but that exception resulted in a failure or an incident or a failure. Okay. The HFACS Accident Investigation Protocol, as I indicated, this is a very formal protocol. The taxonomy itself has formal definitions and formal assignments to various HFACS categories. The HFACS accident investigators have to go through HFACS training and certification before they can use HFACS to classify accidents. So the requirements for the protocol: develop an accident investigation process that focuses on fact finding, not fault finding. The fault finding occurs when we assign the facts to the HFACS through the taxonomy, determining the root causes of why the event occurred, making changes so the event does not happen again, set a policy that accidents and close calls, these are incidents large and small, will be investigated with equal vigor, provide HFACS training and tools to staff conducting accident investigations, and then audit completed investigations to ensure they are being completed on a timely basis with an adequate level of detail. HFACS is no different than planning a quality management system itself. We have the policies, we have the procedures, we have the goals, we have the production, actually Y equals F of X transformation, the control systems, and then the audit feedback. The investigation protocol, we start with a background investigation. This is when an incident occurs or an accident. Review the records related to the incident and meet with the responsible authorities. Then they go to the site investigation, secure the accident scene, determine any physical changes to the scene, and map and photograph the evidence. Interview witnesses, prepare a list of questions that require narrative answers, and conduct interviews in private settings. Analyze the causes and classify in accordance with the HFACS taxonomy, and then reporting, prepare a standard HFACS report conforming to agency guidelines. And when we say agency guidelines, that is one of the branches of the DoD or the FAA, or if you happen to be in healthcare or mining, they have their own reporting guidelines. So that sets the background for the Boeing 737 MAX crash and grounding HFACS analyses. Now, this is the caveat here. This is my analyses. I supervised the HFACS training and classification for my doctoral student in 2014. So my background with classification may be a little rusty, so that's the caveat. These are my assignments based on going back to the taxonomy and making my best assignment for these. But will come out of but they all come out of FAA reports. So on October 29th, 2018, Lion Air Flight 610, a Boeing 737 MAX crashed shortly after takeoff in Jakarta, Indonesia. November 5th, 2018, the evidence emerged of a potential contributor to the accident. The FAA conducted a preliminary risk assessment. So out of the risk assessment, I read through the risk assessment, and then I made these assignments myself to technological environment, going back to here, technological environment right here. And then, of course, there will be some other assignments in the categories. So technological environment, erroneous data from a single AOA sensor activated MCAS and subsequently caused airplane to nose down. Trim of the horizontal stabilizer, that's a root cause of the sensor, resulted in cascading failures. Another technological environment failure, MCAS reset generated repetitive MCAS commands, forcing multiple airplane nose down stabilizer trim commands, i.e. the pilots would pull up, MCAS would push the nose back down. Another technological environment failure, multiple MCAS commands resulted in significant horizontal stabilizer mistrim condition, which the flight crew could not counter using only elevator control. Physical mental limitations. This is going back to physical mental limitations. Right, hang on. Physical mental limitations, condition of the operators themselves. The flight crew was unable to effectively manage the stabilizer movement and multiple flight deck effects that resulted from the single AOA sensor failure. So we had the cascading failures, the multiple nose downs, pull up, they couldn't overcome the trim. Failure to correct the problem, the AOA disagree alert message on the primary flight display was not functional is not functional unless the AOA indicator option was chosen by the airline. This alert message is intended to be standard on L737 MAX, and that was not chosen by the airlines as an option. And then Boeing went back, and that was when the Boeing planes were grounded. That was one of the revisions they corrected. They installed that as a standard option. And then finally, for the 610 crash, another technological environment, an extremely remote FCC failure of the stabilizer system that required timely pilot intervention to ensure continued safe flight and landing. So we had multiple technological environment failures, a physical mental limitation, and a failure to correct the problem. Ethiopian Airlines Flight 302 crash. This was on March 10th, 2019. Also a Boeing 737 MAX crashed shortly after takeoff in Addis Ababa, Ethiopia. Partial data, the altitude, airspeed, and vertical speed was available from a land-based automatic dependent surveillance broadcast system. Again, assigning reading the FAA report and doing the HFACS failure assignments, another technological environment, the 5 Lion Air 610 technological failures from before repeated on the Ethiopian Airlines flight. Notice that they didn't fix them from 2018 to 2019. Of course, the investigation was probably still going on. Another physical mental limitation. Again, the flight crew was unable to effectively manage the stabilizer movement. And then there was an organizational process, the replacement of the AOA sensor that was installed on the accident aircraft had been miscalibrated during earlier repair. So this brings me to my HFACS classifications of the 2 aircraft crashes. They all originated with an organizational processes, again, reading the taxonomy. But notice out of the 4, then had to go through planned inappropriate operations. And then the sensor failure, they failed to correct the problem. Then of the 4 planned inappropriate operations, 3 went to technological environment, 1 went to physical mental limitations, which we've already discussed, and then the failure to correct problem went to the technological environment. So we can see that we had five to start out, how they break apart. And this, by the way, with the hundreds of classifications that my doctoral student did in 2014, we just used the frequency counts as the strength of indication. And then finally, the technological environment and the physical mental limitations all fed into decision errors. And those decision errors resulted in the accident. Now, if we were doing the standard uh, Ishikawa diagram, we would be able to see the decision errors. We may or may not, but we might have been able to see the technological errors, but tracing it all the way back, which HFACS does, all the way back to the organizational influences, those latent factors, we probably would not do that. Questions, comments on the summary? Our one HFACS expert out there, any thoughts on your part? This is an open discussion. As I tell my doctoral students at school and lectures, this is an open debate discussion.
Well, I'm not trying to debate, but I think this is a fantastic way of analyzing these kinds of things. And I've never seen it used at work.
Okay, yeah. And that's why I'm introducing it. Well, not why I'm introducing it here, but I'm introducing it here, setting us up for the next section. Okay, thank you for your feedback. Okay, then we have the Alaskan Airlines emergency plug earlier on January 5th, 2024. We're all familiar with that. Flight 1282 performed an emergency feedback of one of its emergency turnback, sorry, of one of its Boeing 737 MAX 9 aircraft. As a result, blowout of the emergency exit door plug from the left-hand side of the aircraft caused a rapid decompression of the cabin and left a large hole in the side of the fuselage. The aircraft returned safely and there were no injuries sustained on board the aircraft nor on the ground. Now, reading the FAA reports, first, we all go back to Boeing. Well, how could Boeing let this happen? Again, looking at the HFACS classification and working backwards, again comes to organizational processes were not adequate. They were not in place to avert the latent alignment of failure to correct a problem, and we'll get to the problem in a minute. And then the adverse mental states. So skills-based error, Boeing removed the door plug in an unplanned process when some defects were discovered with some rivets. When Boeing line workers reinstalled the plug for reasons unknown, the four remaining bolts, pardon me, were not reinstalled. The bolts became separated from the plug during the removal. So again, HFACS, we would have found, well, it was an unplanned process, so we can assign it back to an operator failure. Typically, that's it's the operator failures, the kind of the catch-all category. I noticed this in some of the HFACS reports that my doctoral student did in 2014, or him and his team did in 2014. So we can trace this again back to organizational processes. Notice the commonality we're starting to find. But on Alaska Airlines part, when you read the FAA reports, again, organizational process, failed to correct the problem, adverse mental state, and skill-based errors. The airframe had reported 3 other causes of pressurization issues on previous flights prior to the January 5th blowout. The incidents were on December 7th, 2023, January 3rd, and January 4th of 2024, immediately before the January 5th blowout. In all cases, Alaska Airlines maintenance crews simply reset the pressure warning lights and system and release the aircraft for service. Now, is this related to the door blowout? Maybe, maybe not. Were the pressure warnings real, or were they, and it's well known in aircraft that you have a lot of false signals, or were they truly false signals? And the warning lights were simply reset. Should there have been a further investigation? Uh, Good question. Yeah, it's interesting that two of those occurred on January 3rd and January 4th before the blowout on January 5th. Now, I do not know if they went back and looked at the on the panel, the blowout panel on these airlines and determined that they were safe or not. But the key takeaway again, notice organizational processes have come to light. So both it appears that organizational processes in the aircraft manufacturing and in the airline industries allow latent failure modes to occur. Questions, comments? Okay, so you say, Dr. Carter, why did you go through all of this, HFACS? What does this have to do with Quality 4.0? I'm glad you asked. So HFACS application to failure, future Industry 4.0 failure analyses. Industry 4.0 is the evolution of Industry 3.0 automation asymptotically, as Milt noted earlier in his discussion, and I found in my research and in surveys of industry, out there in the industry, healthcare, government, everybody knows that this thing called smart cyber physical systems is coming down the track. They don't know what it is. They don't know how to implement it. And a conference I was at in November, I sat down and talked with a couple of our industry partners, and they both told me the same thing. And I kept it specifically to AI because cyber physical systems are smart because of AI, but you have to have the autonomous robots, the big data analytics, the data science, the Internet of Things, augmented reality, additive manufacturing, cybersecurity, simulation modeling, the digital twins. All that has to come together in a package. So I asked them about AI, and in both cases they said, we don't know what AI is. We know it's out there, and the best we're doing right now is doing our research, identifying potential applications. We'll put it into R&D a while, see if we can develop an application either that benefits our process or benefits our products. And if it does, we keep it. If it doesn't, we scrap it, and then we go look for the next AI application and try it again. So as Milton indicated, it's really a trial and error process right now. There are no strategic plans, so to speak. Now, maybe the people that are pushing AI, maybe Microsoft, maybe Google, IBM with their quantum computing, they have some strategy. But for the average person in industry and healthcare and services and in government manager, they are struggling with what is it and how is it going to affect the performance of my organization, specifically ROI versus any technological advantages that I might get out of it. So when we talk about AI and all of this, it's not, or we talk about Industry 4.0, we're talking about smart cyber physical or smart cyber technical systems integrated into the organization. But it's toward massively, this is the key term, horizontally, vertically integrated distributed manufacturing that is planned, executed, and controlled by artificial intelligence, cyber physical systems themselves, i.e., we're taking the humans out of it as much as possible, using cognitive computing over the Internet of Things, cloud computing. The goal is intelligent distributed manufacturing, where the most capable, efficient combination of HFACS, smart cyber physical transformation processes can be negotiated at any instant of time t by the smart physical systems themselves. Somebody has their mic open. Thank you.
Puts others first, and the team captain is by his side.
The
The situation couldn't be
Mr.
more
Mr.
serious.
Coog,
Medics are helping someone fight.
can you close your mic? Thank you.
Sorry.
That's okay. Thank you. So think in terms of massively horizontally vertically integrated systems. So Industry 5.0 is not really a trail of revolution, but it constrains Industry 4.0 horizontally vertically integrated cyber physical manufacturing to achieve the most capable, efficient combination of Y equal F of X processes that support the evolution of a human-centric, resilient, and sustainable society. So currently, has anyone seen any work on the RAMI 4.0 model? RAMI 4.0 is being developed in Germany, supported by the German government as the layered approach. How many of you are familiar with the current internet 5 or 6 layer model? I forget what it's called now, but they're modeling after the current internet model. So the most advanced development of Internet of Things model for massively horizontally vertically integrated distributed manufacturing is the RAMI 4.0 framework. It has layers on the left side that range from the asset, the manufacturing asset or the product itself, up to the business strategy itself. So it's taking in consideration the vertical layering of the business from its strategy all the way down to its actual production of production processes. On the right-hand side, hierarchy levels, those levels are from the product to the field device, to the control device, to the stations, the work centers, the enterprise, and then finally the connected world. This very much reflects the current, is it iOS? I've forgotten. It's been a long time since I've dealt with that model, but the current internet model. Then finally, then on the left-hand side at the bottom, we have the life cycle value stream. We have the typology. This is the theoretical framework. And then the instantiation of the typology. So this is the layered framework under which the Internet of Things is most likely going to evolve. What does that mean for us in terms of failure analysis? Well, the IoT RAMI 4.0 framework infers that manifest and latent moderator and mediator failure causes can occur across multiple business and hierarchy boundaries. So we talk about massively horizontally vertically integrated. This is the contracted manufacturer here on the right. This is who delivers the product, the final product to the customer. And using the massively horizontally vertically integrated manufacturing worldwide, that we can, for process step 1, process step 2 through process step, we'll call it N-1, because the manufacturer itself is N, the smart systems themselves can negotiate any path through this for the production of the finished product, and they're choosing the most efficient, most effective production point and the most cost-effective production point. So when we talk about horizontally, massively, vertically integrated, we're talking about this type of integration. Also, notice that I have copied the RAMI 4.0 model, because the RAMI 4.0 model will have to be integrated or implemented within each organization and between organizations. As Milt pointed out earlier, this is not going to be uniform. The implementation of data science within either quality or within the organization is not uniform, because there are differences in organizational history, organizational culture, organizational background, organizational products, organizational capabilities, organizational services. That means each of these will be in different states of implementation and capabilities. So when we talk about being able to do fault tree analysis, we have to be able to trace from the failure at the customer side back through the particular combination of processes that were used at the given time over the Internet of Things. Are we okay with this? in relation to the RAMI model. Any questions or comments? Okay, so this brings me back in August of this year. I made a presentation on my proposal to an approach to Quality 4.0 data science. I'm trying to find that over here. In that approach, I noted that we're typically following, in Quality 4.0 is typically following the business analytics model of big data. We try to find useful patterns in the data and then implement them. There's also been some work on, if I recall that discussion, on experimental design within data analytics. But again, it's not really organized as Milt indicated earlier. So from that work, I analyzed or I decomposed the variance components of Industry 4.0 design and control and the added variance components of Industry 4.0 Internet of Things. So the manifest and latent moderator and mediator failure causes of the IoT RAMI 4.0 framework reside in the sigma square Yij Industry 4.0, that is right here. And that's the systemic, self-enhancing, self-evolving, and co-evolving evolutionary variance components, i.e., going backwards here, each one of these are a system, and they exist within a system of systems. And each one of these systems will have to, if you're familiar with systems theory and systems of systems theory, there are three states that a system must be in order to remain viable. First of all, it has to self-evolve. That is, it has to improve its own internal processes and self-delineate from its external world. That's called complexification. Then, once it has done that successfully, it has to identify the external forces in the competitive environment and respond to those by evolving new capabilities. So we have the self-enhancing internal evolutionary processes, and then the evolutionary processes due to external forces. But within the Internet of Things, it has to co-evolve with other organizations, RAMI models, in order to be able to communicate with them effectively and be the most efficient, the most effective production, on the most efficient productive path through this model. So the Y sub ij are the systemic, self-enhancing, self-evolving, co-evolving evolutionary variance components of each RAMI system itself. The Y sigma square Yk sub Yk are the systemic variance components that impact smart products, processes, and services horizontally, systemic feedback and control, i.e., we're going to have differences in the physics of the process and the efficiency of the process, differences in the communication protocols across the various levels. So all of these present variance components that can be induced latent variance components that can be induced into the manifest failure of products that are delivered to our customers. In services, control of Y equals f of xz. Notice we have the z there for the latent failure modes, either the mediator or the moderator variables. Performance, stability, robustness, functionalities. Now notice, how many of you took control theory undergraduate? If you'll recall from undergraduate, there is a trade-off between performance and stability. I can increase the gain, the performance gain, but I do that at the expense of stability. I can fine-tune a production process so it will perfectly produce one product one product characteristic only with minimum variance, but it will be highly unstable. Or I can decrease the performance and increase the stability. And then robustness gets back at the concept of perturbations induced into the system. So there is a performance, stability, robustness trade-off that will still exist in the Industry 4.0 cyber physical systems. We cannot get around that. That's the physics of the world we live in. So that the feedback, the analysis that we have to do across the massively horizontally vertically integrated, or will have to do across the massively horizontally vertically integrated systems, must be both horizontal and vertical, and it must allow the mapping of latent defects to our physical manifest defects at the customer side back to their latent causes within the RAMI 4.0 hierarchical framework. And then, of course, the sigma square yi is the Industry 3.0 design and control variances. If you attended the August 21st, my August 21st discussion, no design is perfect. We like the Y equals F of X model, but that assumes a one-to-one bijective mapping, and we rarely have bijective mappings in our designs. And then the sum of sigma square measurement error on the end. This is separate work that I've been reading, but across the Internet of Things, we have to, well, currently measurement system analysis, if you're familiar with it, is done inside four walls, and you do it across processes. But now we're going to have to do it across organizations, and there are additional variances that can accumulate across those organizations. So let me do a wrap up here. We're coming up, give you 10 minutes. With its focus on human systems induced failures and layered approach to explaining the root causes of how accidents occur across organizational levels, the HFACS model can be adapted to the RAMI 4.0 layered IoT protocol model to identify manifest and latent causes of failures across levels and boundaries of the massively horizontally vertically integrated cyber physical systems. Ultimately, as Milt noted earlier, smart cyber physical processes are designed and created by humans and must exist within human organizations. That's why I call it cyber technical socio. Manifest and latent failures and their root causes will occur, guaranteed will occur across massively horizontally vertically integrated distributed fiber physical systems production. The impending need already exists. So this is my recommendation, and this is really to, I don't know if it's to ISO, if it's to ASQ, ISO, ASQ, ANSI, but form an Industry 4.0 quality technical committee to transform the HFACS failure model and investigation process into an industry quality 4.0 RAMI failure analysis and classification system that we can apply in the future. Well, not only apply, but evolve and apply across organizational levels and boundaries, possibly with future AI support. I see Michael came on. Questions, comments?
Yeah, it's kind of a, Stephen, a great presentation, and thank you. Just going to share some comments that I have seen. There are two questions really, but I'm going to put them in one because I think that they're related. First one is how to get the buy-in from team for this kind of application, because some people tried and it was challenging to implement with the team. And second,
are we talking about the HFACS or my recommended
HFACS?
Oh, okay.
And the second one is how to HFACS to incorporate in design process to prevent failures. So kind of, I think that they're related. That's why I combined them.
Yeah, you're absolutely right. They are related. This is this gets back at the organizational need. The HFACS has evolved. It is heavily used by the DoD, the Air Force and the Navy, and by the Army. FAA, and it is the standard. Well, FAA has its standard accident investigation, which is then put into HFACS. It is evolved and it has been standardized in those. It is struggling, and this gets at the question of how do you get teams or organizations to adapt it. They have to, that's the key word, is adapt. That's why it's been tried in mining, it's been tried in transportation, it's been tried, and there's a lot of effort being driven in healthcare. It's going to take a champion that builds a group that champions it within an industry or within a sector. It's not there fully yet in mining. It's not there fully yet in transportation or healthcare. But there have been a lot of publications in healthcare in the last 10, 15 years proposing an HFACS-like system. So the answer is there is not an organized effort. It's going to take someone to champion it.
Thank you. And another thing is kind of, if I can comment, is usually if you're in a business, this kind of analysis has to be performed very quickly, and that becomes challenge because people want results. So similarly to failure mode defect analysis, fault tree analysis, and this whole process, the best practice is really to do that before the event. And you use this as an additional knowledge, because this is a knowledge management within organization. Question is kind of how well is designed, depends on the level of knowledge that people and team have. And as I was looking this presentation, I never was exposed to this tool, and this is one of seldom tools that I have not been exposed. But I was thinking really kind of, you can think for failure mode defect analysis, how you use a chat GPT to identify potential failure, because model that Stephen presented probably has number of layers going down. This is a kind of high level, and devil is in details. You have to establish linkages and drill down. But use a chat GPT to give you idea and work with the subject matter team together what are potential failure, and then you use the data mining to analyze, for example, principal component analysis, which of those factors relate to each other. So it's a beautiful, we as a quality professionals have a great opportunity really kind of with the quality 4 to add new tools and methodologies to what we do right now. Because if you look at the Lean, if you look Six Sigma, if you look at the root cause analysis, if you look at the failure mode defect analysis, that's all part of quality 4. Now we just have a new technologies and tools to add on top.
Yeah, absolutely right. And right now, ChatGPT is the poor man's AI, and it's the best we can do. I think as we move forward, you're going to see more and more AI support. I know I use Semantic Scholar for a lot of my searches. I also still go through the ODU Perry library because they're connected to so many databases. But yeah, you're going to see a lot more AI support for these tools, and I think that's where AI is going to come in as a human support mechanism, so that we're leveraging it. Will we get to the AI talking to AI, super massively, horizontally, vertically integrated manufacturing depicted here? Well, I think that's possible, but it's also an asymptotic property. I think we're going to approach it, but never really get there. So
Okay.
that's a good plug. I don't know if you're still teaching, but I'm looking for doctoral candidates to do research in this area. So anybody interested, I'll throw in my plug there. I didn't put my contact information, tcotter@odu.edu. Send me an email.
Thank you. Thank you for a great presentation. And that brings us to the last one that we have for today.